Hello again. All right, so we're going to talk a little bit about balance. We've covered kidneys, we've covered lungs, so respiratory and renal. So we want to talk a little bit about homeostasis. We've still got some digestion to talk about, but I want to kind of take a break and really talk about how we're regulating some things like water and salt and acids and bases and things like that. Then we're going to get into some acid-based problems, and then we'll get to digestion. So kind of taking a little break here just to really make sure that we're taking these organ systems and thinking about how they work together. We're getting toward the end of the semester, and so it's really time to really start thinking, okay, all this stuff that I've learned, how does it all relate to each other? How do these things work together to maintain homeostasis? And so one of the things that's really important is water and electrolyte balance, and also acid-base balance. And so for those of you that are going to go into the clinical world and health sciences and be nurses and things like that, one of the things you will be monitoring is fluid output and fluid input. How much are they drinking? How much is your patient urinating? You'll be measuring how what the respiration rates, what's their blood pressure. And we know that blood pressure and blood volume has something to do with water intake and water output, so we know the kidneys can help control that. So just one more kind of look back and to make sure that we're integrating that and not just thinking of it as this is the kidney, this is the lungs, and remember all of these things are working together. Remember, if you think about the body, you've got about 40 liters of water in the body and an average adult male. About two-thirds of it is going to be intracellular and the other third is extracellular. And so if you think back, this is taking you way back to the first couple of lectures in anatomy, way back at the beginning of Unit 1, and we talked about how your body is full of water. And if you think about your total body water, that's divided into what's inside the cells, okay, the intracellular fluid, and then what is outside the cell, okay? And what's outside the cell includes that fluid that bathes the cells, called the interstitial fluid, the fluid that makes up the plasma, the fluid that's in the lymph, and then what's called transcellular fluid that's kind of moving through the cells. So you have what's inside the cells and everything else. So intracellular versus extracellular. So most of your water is actually inside your cells. Okay? And if again, here's just another look at it where you can see most water is inside the cells. Now, another key importance when you're looking at fluid balance is what electrolytes are found where. Where is sodium? Where is potassium, calcium, magnesium, chloride? Your major electrolytes, those ions. And so we talked about this some when we talked about membrane potentials, and we talked about action potentials, and we talked about the movement of sodium, the movement of potassium to generate that electricity. So yeah, we've done it before, so yeah, you can't just forget about it. So if you look here, you can say, where do you find most of the sodium? Most of the sodium is in the extracellular compartment, and most of the potassium is in the intracellular compartment. So if you can draw your picture and go, is sodium higher on the outside or the inside? So you go, okay, sodium is going to be in the extracellular, so sodium levels are higher on the outside, potassium levels are higher on the inside. Okay, calcium, is a little bit higher on the outside than the inside, but not by too much. Magnesium, there's more on the inside than the outside. Chloride, more on the outside than the inside. Bicarbonate, phosphate, and sulfate. These are our key players right here. We want to really focus on sodium and potassium, because why do we care about sodium and water? Water follows sodium. So if you know what your sodium concentrations are and where they are, we know that's going to hold on to the water. Well, that's an important thing to know when you're thinking about water balance. When we think about the movement of fluid, we want to remember how all these different compartments, the intracellular, the extracellular, the plasma, the tissues, the actual cells, and think about how that fluid is moving. So I've got you a picture here just to show you all those compartments and how that water is moving. And remember, when you have the movement of water, it can move through osmosis, and it can also move due to hydrostatic pressures. And so remember, hydrostatic pressure pushes, We talked about this when we talked about glomerular filtration rate, and osmotic pressure sucks, pulls it back in. So remember those big plasma proteins that are in the capillaries after the blood has gone through the glomerulus, those big plasma proteins suck the water back in. So you have a balance of water movement due to hydrostatic pressures and osmotic pressures, okay? And this kind of, I'm not going to read this to you because you guys can read, but this tells you where this is occurring, where the hydrostatic pressures are working or the osmotic pressures are working, and so forth. And we've done this throughout the semester, talking about, again, movement in and out of capillaries and in the glomerulus. This is kind of a, you should already know this, but I never assume anything. I've learned not to assume anything. We know that water has to be balanced, so what comes in must go out. So where do we get most of our water? Well, we drink it. So most of our water is in beverages. Then you have about 30% in food. So think apples and, all your food most of your food has got some kind of moisture in it. And then 10% is metabolic. So your body's producing its own water. Okay, so this water in the food and beverages is really where you regulate your intake. We can't really consciously regulate metabolic water, but we can get some water and either hydrate or stay dehydrated, depending on your situation. If you're about to get in the car for a 6-hour ride, you may try to stay dehydrated, but you can regulate how much comes in just by drinking and eating foods that are high in moisture content. Now, it's got to go somewhere. Where does it mostly go? Well, most of the water is lost via urine. Some is through the skin and lungs. So when you blow out that moisture, that's the vapor, plus your skin's always a little moist. You're losing it through the skin and sweat. Or through the skin, sorry, just kind of evaporating through the skin. About 6% is sweat and about 6% in feces. Now, this number can change, go up or down, depending on temperature. Are you sweating or not sweating? The water in the feces can go up or down, depending on if you're constipated or have diarrhea. Okay, this doesn't really change. The amount of water lost in your skin and lungs stays kind of about the same. And then this will change and go up or down, depending on how much you drink or don't drink. So you have to take this all in context, put everything together. Okay, so think about water and electrolyte balance. Foods are a source of water, so I guess that's right, the H2O, and ions, electrolytes. Your fluids are going to have water and some electrolytes. I think Gatorade would have electrolytes in it. And then your metabolic reactions, what your body's actually producing itself. So your food and your fluids, that's going to be input, and that's got to balance output, and the ways you get rid of that is either through sweating, feces, urine, and again, to some extent, your skin and lungs. Okay, so water in, it's got to equal water out. Now, not only is the water got to be balanced, the ions have got to be balanced. And we're going to focus on just a couple. There's a lot of ions. We're going to focus on just a few. Potassium and sodium being the most important, because again, those, especially sodium and potassium, play a role in action potentials and nervous conduction. And so in order for our nervous system to work, we know we have to have these two ions in balance so they can work and allow us to generate membrane potentials and all that good stuff you've learned about before. But sometimes you can get out of whack. You can have too much or too little. And so the disorders of potassium and sodium are hypokalemia and hyponatremia. So this is not enough potassium and this is not enough sodium. Hyperkalemia is too much potassium and hypernatremia is too much sodium. So the kalemia and natremia, that's where you get the K and the Na. Those are the original words that stood for sodium and potassium. Okay, and so before we came up with sodium and potassium, it was kalium and natrium. So if you have, we've already talked about how we can balance this, how we can regulate it. A lot of it's under hormonal control. So for example, if you have a potassium ion concentration that's going up, your adrenal cortex is going to be recruited to release aldosterone. That's going to cause the renal tubules to reabsorb sodium and get rid of potassium. So you're going to hold on to your sodium, get rid of your potassium, and bring your potassium back down. So we've already talked about that. I'm just reminding you that we've already talked about all this. Okay, we've talked about the different hormones and how they regulate some of these different ions. And these are the disorders that are associated with those ions. Same thing with calcium, also very important. Remember when we talked about, again, you think back to the neuromuscular junction, way back, and remember you have to have calcium come in to open up and allow the acetylcholine to be released, to release your neurotransmitters. We know calcium is important for bone health. It's important for muscle contraction. If you have too much, hypocalcemia, too little, hypocalcemia, too much, hypercalcemia. Again, we've talked about this before. We know that you've got to get calcium into your diet, and it's going to be stored in your bones, and it can be moved from your blood to your bones. And we've talked about parathyroid hormone and calcitonin. So take a minute to review that. So you have a low amount of calcium, your parathyroid glands are going to be stimulated. You're going to release PTH, and we know PTH does several things. It causes you to increase the amount of calcium that you can absorb from your diet in your intestines. That's going to put more calcium in the blood. It's going to cause your osteoclasts to increase. That's going to also bring your calcium level back to normal. Your renal tubules can conserve calcium. So all of these work together to control calcium. So go back and look at that. These are things we've talked about. I found that when I assume that you guys remember or critically thinking and kind of bringing all this information back together, that sometimes that doesn't happen. So this is kind of this is one of those system connections in a little more detail. All right, so your acid bases, we know you've got to regulate that as well, because acids and bases really are just hydrogens and hydroxyl ions. So if you have an acid, you're going to have the release of more hydrogen ions. If you have bases, you're going to have more hydroxyl or OHs. We know that acids and bases can react. This is sodium hydroxide, which is a base. This is hydrochloric acid, which is an acid. If you take an acid and you take a base and put them together, the output of that is a salt and water. So sodium hydroxide plus hydrochloric acid, they will neutralize each other. If you put an acid and a base together, they will neutralize each other and form a salt and a water. And it can be any salt depending on what the base and what the acid is. It can be a different salt, but it's going to come up with salt and water. If you've had chemistry, then you've done this before. We also know that if you take carbon dioxide, which is considered an acid, and in the presence of water, it will form something called carbonic acid, and that will break apart into a hydrogen ion and a bicarbonate, which is a base. We talked about that a little bit when we talked about respiration. So just as a reminder, again, I don't assume anything anymore. We know what pH is, right? So pH is that 0 to 14 scale that is measuring hydrogen ions. It's measuring how much hydrogen is in the solution, okay? The more hydrogen you have, the lower the pH, the more acidic it is. So it's going to be 0 to 7. The least amount of hydrogen you have, or you can say the more OHs you have, the higher the pH. So the more basic it is, which is going to be 7 to 14, okay? When we think about our blood, our normal pH in our blood is between 7.35 and 7.45. So it's slightly alkaline. That may surprise you. So our neutral pH for our blood is actually 7.35 to 7.45, which is a little bit on the alkaline side. And this is one of those you've got to memorize. I don't make you memorize too many numbers, but your normal blood pH is something you need to remember. So where do we get all those hydrogen ions? What's adding acids to our body? We know that when you undergo aerobic respiration making ATP, there are things called carbonic acids. When you do anaerobic respiration, you can get lactic acid. If you are breaking down fats, you can get ketone bodies, which are acidic. When you break down amino acids, you get sulfuric acid. When you break down some proteins, nucleic acid, you get phosphoric acid. Your stomach has got hydrochloric acid in it, and that can be absorbed through the digestive tract. So there are a lot of acids in your body. Well, but your pH is 7.35 to 7.45, which is alkaline. So if all of this is causing your blood to become acidic, how come you're not acidic? Why is your blood pH not below 7? There's got to be something that's neutralizing it, right? We've talked about this. All right, we control pH, right? We have a buffer system. So I know we talked about this at one point where if you have heartburn, you can take a Tums and that will neutralize the acid in your stomach. You basically have that going on in your bloodstream. You have a natural buffer system in your bloodstream that will help you resist changes in pH, keep your pH pretty normal between 7.35 and 7.45 by either grabbing those hydrogen ions, okay, or releasing those hydrogen ions. So if you need to become more acidic, you'll release hydrogen ions. If you want to become more basic, you'll grab those up. So if you have all of these things that are producing acid, we want to grab all those H's and get rid of them and neutralize them. So we do that using bicarbonate, okay? So bicarbonate is our buffer. We also have some, let's see, let me go back to here. I lost my train of thought. So this acid buffer system, which is basically bicarbonate. There's some other ways that we can neutralize as well. Proteins act as buffers, and we have natural proteins in our body, then they will bind and release hydrogen ions. That helps us control pH. We have some phosphate molecules. This is kind of our primary, and then these would be kind of lower down the list with the proteins and the phosphates. If the blood plasma, of the bicarbonate in the blood plasma is not enough to really deal with that, then we can also depend on our kidneys and our lungs to help us balance it as well. So we can excrete carbon dioxide, we can breathe more out, and we can excrete hydrogen ions from our kidneys. So we can rely on our kidneys and our lungs to help us with our acid-base balance. All right, so you really have several different ways to help regulate pH balance. And it's really important. Your body's functions are very tied to that pH. You don't work well outside that narrow pH limit. So when you think about that buffer system, the buffer system that we have in our blood is that carbon dioxide and bicarbonate. And we talked about this before, where you have carbon dioxide plus water gets carbonic acid, which can break down into hydrogen ions and bicarbonate. And this reaction can go in both directions. We talked about that. So if you need to release hydrogen and make your blood more acidic, the reaction goes that way. If you need to make your blood more basic and get rid of hydrogen ions, the reaction goes that way. I know we've talked about that before. Let's see. That's all I was going to say there. Just a reminder, because I know we've talked about it before. So how do we do that from the lung standpoint? So when we're increasing our breathing or decreasing our breathing, we're changing how much CO2 we're either holding on into our body or breathing out, right? So you can change how well you're ventilating to change how much CO2 you're getting rid of. So if you're breathing kind of fast and deep and you're getting rid of a lot of CO2, you're driving that equation this way, which is going to be taking the hydrogens with it. So what will that do? It's going to raise the pH. It's going to become more basic. Okay? So the faster you breathe, the more CO2 you breathe out, the more hydrogens you're going to leave, and that's going to leave you more base. Okay? If you hold your breath or don't breathe, more CO2 stays in your body. The equation goes that way and releases more hydrogen into the system, which is going to lower your pH, make it more acidic. Again, this is hopefully a review. We've talked about this. We know the kidneys can also do this by excreting more or less hydrogen. So you can get rid of, or bicarbonate. You can get rid of bicarbonate in your urine, and you can get rid of hydrogen ions in your urine. All right? So the other values that you need that are really important when you're talking about acid-base balance, not only if you're talking about, you need to know pH, but we know that you can balance pH using your lungs or your kidneys. And so if you're doing that, what values do you think you should know? What would be a good lung value to know? How much CO2? That'll be a good thing, because that's one you can change with your lungs. And then your kidneys, you can change bicarbonate levels. You can excrete or hold on to more bicarbonate. So these are the normal values in your body of carbon dioxide and bicarbonate. So 35 to 45 and 22 to 26. You don't have to memorize these. I'll give them to you. If you were to take someone's blood, I guess a lab value of their blood, and look at their CO2 levels, if they have too much CO2, we call that acidosis. Okay, respiratory acidosis, because CO2 is controlled by the lungs. So too much CO2. So let's go back. So too much CO2 is going to drive it this way, right? So acidosis. Low levels of CO2 means you're blowing it all off. That's going to drive the equation the other way, respiratory alkalosis. Okay? If you have a lot of bicarbonate in your blood, right, a lot of base, metabolic alkalosis. So anything that's going on in the kidney we call metabolic. So respiratory versus metabolic. If you don't have enough bicarbonate, then that means you're not able to gobble up all those H's. You're going to have metabolic acidosis. I know? All right. So what you're going to do, we're going to do some problems, and what you try to understand is if a patient comes into your clinic and they're in distress, and you take a blood sample and you find out that they have a pH problem, that they're either in acidosis or alkalosis, we've got to figure out, are they in alkalosis or acidosis because something's going on with the kidneys or something's going on with the lungs? Is this person coming in and they're hyperventilating, or they're hypoventilating? Are they in kidney failure? What is causing their blood pH to shift? So that's the first thing you got to figure out. You also have got to figure out if you're coming in and they've got a lung problem, so they're not breathing well, they're having some kind of an issue with their CO2 levels. We know that our body tries to stay in balance. It tries to maintain homeostasis. And so what you find out is if you're having a respiratory issue, your kidneys may be working to try to fix the problem. And we call that compensation. When the organ system that's not really involved, where there's no problem, is trying to fix the problem for the other organ system. Does that make sense? So pH problems caused by one body system can be compensated by the other. So if it's a lung problem, the kidneys are trying to fix it. If it's a kidney problem, the lungs are trying to fix it. All right, so for example, if your CO2 levels are high in body fluids due to hypoventilation, that would be respiratory, then the kidneys, they're going to try to fix that by retaining more bicarbonate, okay, the base. If your bicarbonate levels are too high in the body fluids, then your breathing is going to change. It's going to slow down to hold on to CO2 to bring the pH back down. So your two organ systems are really working hand in hand, trying to help each other out, and we call that compensation. So if one organ system is working to help the other organ system has malfunctioned, then that's called compensation. All right. Now, when we think about compensation, we have what's called full compensation and partial compensation. So full compensation means if someone comes into the lab and you take their pH actually looks normal. Everything looks normal, and you would not really know that there was something wrong unless you were looking at the CO2 levels and the bicarbonate levels, and they are not normal. Okay? They are out of whack. They are not in their normal range. If they're not in their normal range, that's telling you that one of these organ systems is trying to fix the problem. It's trying to compensate, and it has compensated because the pH is normal. Okay? If you have partial compensation, that means the pH is a little out of whack. It's not quite normal, all right? And you've got to figure out if which system is trying to fix the problem, okay? So the system that's working correctly is trying to fix it, but it cannot overcome the malfunction. It cannot compensate enough to bring that pH back to normal. So it's only partially compensated. It just can't do the job. I think this will make a little more sense when we do the problems as well. We'll kind of work through it again. So when you think about acid-base problems, remember it's kind of multifactorial. There's many things going on to keep your acid and bases in balance. And the first thing that happens is your chemical buffer system. the bicarbonate, the phosphates, and the proteins. Okay, that's the first thing. Those are in your blood and they're rapid. They can work and they can buffer everything as fast as it needs to be. If there's an additional problem, then you have to go to your second line of defense. So this is our backup plan. And the backup plan is either to change our respiratory rate or change our bicarbonate hydrogen levels using our kidneys. Okay, that's our backup plan. All right? So let's give some examples of how this would work. So let's say you have an arterial blood pH either drops or rises for a couple of hours. Well, let me say that again. If your blood pH drops to below 6.8 or rises above 8.0, a person can't survive for more than a couple hours. Okay, that's a pretty big shift. You can't really make it. So 735 is your happy place to 745. Okay, you can live a little bit to the alkaline side, a little bit to the basic side, but really not for very long. And if you get this far acidic, you're not going to make it. This far basic, you're not going to make it. We got to get you back into balance. So what are some reasons that you could have a pH shift? What could cause your blood to become acidic? What could cause it to become alkaline or basic? You could have an accumulation of acids. That would cause your blood to become acidic. A loss of bases. If you get rid of all your bases, that would also increase the amount of hydrogen and cause you to become acidic. If you lose acids and accumulate bases, that means you don't have as many hydrogen ions and you become alkalotic. All right? So it's all about the movement of that hydrogen. Too much hydrogen causes you to be acidic. Not enough hydrogen causes you to be basic. Things that can cause respiratory acidosis. All about breathing. You're not breathing. Your airways are obstructed. You have decreased gas exchange. All of that will cause your CO2 levels to increase, and that will cause respiratory acidosis. Metabolic acidosis is going to be due to kidney failure. Okay, another example would be if you have diabetes mellitus and you're starting to break down fats and proteins and getting those ketone bodies, which are acidic. All of that's going to increase the amount of acids you have in your body. Non-respiratory acid has nothing to do with CO2. True acids in your body, they're accumulating. You get metabolic acidosis. You're starting to lose too many bases, okay? I'm sorry. If you lose too many bases due to something like diarrhea or vomiting, that will lead to metabolic acidosis. So kidney failure, uncontrolled diabetes will lead to metabolic acidosis, prolonged diarrhea, prolonged vomiting, all of that will lead to metabolic acidosis. I forgot these arrows are going in two directions. So this causes acidosis and that causes acidosis. Respiratory alkalosis, if you're hyperventilating, if you're hot, if you've got high altitude, maybe you've been poisoned, it causes you to hyperventilate. You'll get rid of too much CO2. That'll cause your carbonic acid levels to decrease. That will decrease your hydrogen and cause you to be alkalotic. All these have to do with breathing, so respiratory alkalosis. Metabolic alkalosis is anything other than breathing. So maybe you've got stomach issues, maybe you're vomiting, you're getting rid of all your hydrochloric acid, you're losing your acids, and that's going to cause you to become alkalotic. All right? Let's see. Okay, so I'm going to stop there, and we're going to actually do some acid-base problems, and we'll kind of talk through these things again as we move through the problems. All right, so hang on.